Welcome to lecture number 19 on the subject of VLSI design KEC 072. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. Today, we are going to start a new topic which is known as or based on semiconductor memories. Okay. So, memory element in any semiconductor device or for that reason in any electronic device plays a very important role, because for implementation of any circuit or device you first need to store the data in some reliable location. You might have to update that data also, and you might have to fetch that data also. Both these operations either simultaneously or one by one are implemented by the use of semiconductor memories. It is quite an interesting fact to note that in any on chip circuit or a SoC or a system on chip circuit, the memory element or the portion of the circuit or an IC which stores data generally requires more number of transistors than the area which is computing the logic of the circuit requires. Okay. So, a large portion of any module or any system can generally be taken up by the storage element only. Okay. You can have two dimensional storage elements where you have one row with each cell located, where each cell stores one bit of data. You can have two dimensional structures where you have a row and a column, where an intersection of a row and a column basically tells you one particular location where one bit either 0 or 1 is stored. You can also have a three dimensional arrangement where one row will tell you the location and the other two dimensions will actually be an array of memory. Okay. So, you can have one location, that location has to be specified, that location will store the data, that data might have to be updated or fetched. Okay. So, every memory structure, memory circuit or memory element will have two things. One is the address of that memory, where the data is located or has to be updated. Second, the data itself. Okay. These two things are also used or interchangeably used by notations like word line and bit line. Okay. The level of memory requirement we have these days, it can't be implemented by a simple block of memory. You would need what is known as an array of memory. Okay. So, that basically produces a compact version of a storage element such that where lot of data can be stored in a small volume. Okay. So, these arrays are capable of storing large quantities of digital information, which is essential for the reliability of any digital system. The ever increasing demand for larger data storage capacity, okay, many electronic devices are compared in terms of how much data they can store or accommodate. Okay. This requirement has driven the fabrication technology and memory development towards more compact design solutions and towards higher storage densities. So, the maximum realizable data storage capacity of single chip semiconductor memory approximately doubles every 2 years. This is a sort of trend which has been continuing for a very long time. Okay. There are some design criteria, or you can say the performance metrics associated with any semiconductor memory array. The area efficiency of the memory array, that is one parameter. Okay. What it basically means? It means the number of stored data bits per unit area. This also determines the overall storage capacity and the memory cost per bit. Okay. So, how much cost is there for storing one bit of data? That is one performance metric. Another is what is known as the memory access time, that is the time it takes to either store and or retrieve a particular data in the array. Okay. These two operations, the first is known as write operation where you are storing the data, and second when you are retrieving the data, that is known as read operation. Write and read can be done separately or they can be done simultaneously. They can be done on the same memory location, they can be done simultaneously on multiple memory locations also. Okay. So, this access time basically determines the speed of memory. Okay. That is a very important and a very well known performance parameter. Next is how the memory or the how the data is being stored or fetched, the mechanism of it, especially the storage mechanism, decides what type of memory we are dealing with. You can store the data in a static way, you can store the data in a dynamic way. Okay. This is slightly similar to the static and dynamic sequential circuits which we have also studied, right. If you remember, most of the dynamic version of circuits used some kind of a capacitor for charge storage. The same applies to memory elements also. A dynamic memory element would have some kind of a capacitor across which you have stored your data, okay, or from that capacitor where the data was stored, you are fetching that data. Okay. That is a dynamic way of reading and writing, right. So, you have two basically variants, static and dynamic, and these are the major design criteria, or you can say performance parameters, which basically describe your memory elements, right. Let us just see a general classification. Broadly speaking, memories can be divided into two categories. One is known as ROM or read only memory, okay. And the next is what is known as read write memory or a random access memory system. Okay. ROM, as the name suggests, read only memory, basically what it means is that you can only fetch the data and you cannot update, although you can do the writing operation, but that is usually a one time exercise, and ROM itself can be classified into different categories: mask programmed, programmable ROM, erasable programmable ROM, electrically erasable programmable ROM. So, these are basically the various techniques, okay, on the basis of which you can basically classify or the way you can write the data in your memory. This is a non volatile type of memory. So, the data remains in the storage even if power is turned off. Okay. The counterpart of ROM is what is known as RAM or random access memory. It can broadly be classified into two categories, static and dynamic version, that basically they are both differentiated in the way how data is being stored or maintained or fetched. Okay. This is a volatile type of memory. So, as long as power is on, data is available to you, and when you turn off the power, then it is lost. Okay. So, let us see how a typical memory array looks like. You are looking at a two dimensional arrangement, okay, where one side tells you the rows and the other side tells you about the columns. Okay. This is a row by column approach or a matrix type of a design, where these rows basically tell you the addresses, okay, along with the columns. So, if you start from particular row and you hit particular column, that point of intersection is a particular memory location or a memory cell, and each cell can store one bit of data. Okay. So, if you have here say n address bits, n number of or an n bit address, okay, you can have 2 to the power n address locations in the row. If you have m bit column address, you can have 2 to the power m number of column lines, and this number, the product of this number. Okay. So, if you have 2 to the power n address locations or row address locations multiplied by 2 to the power m column address locations, this product basically tells you about the size of the memory. Okay. So, you need some extra circuitry which is also known as a decoder circuitry, which is going to tell you which location has to be accessed. Okay. And once you access that location, you can either write into that location or you can read from that location, and depending upon the speed of your memory or your level of design, you can access multiple cells at the same time, and you can do multiple read and write cycles at the same time. Okay. So, most of the memory circuits which we are going to discuss, or most of the examples which we are going to go through, have this general structure. Okay. So, this is a typical memory structure where you have a row arrangement and you have a column arrangement, and wherever your rows and columns intersect, you are basically hitting a particular memory cell. Okay. And the size determines how many row addresses you have, how many column addresses you have. Okay. That basically tells you the size of the memory, right. So, now let us discuss what is read only memory or ROM, a common example of non volatile memory. How does it work, how it can be implemented. Okay. Usually writing is a one time exercise, and most of the design is generally based on how you read from a ROM. Okay. So, in that case, in that sense, you can consider a ROM as a simple combinational Boolean network, okay, which produces a specified output value for each input combination. So, you give a particular address as input, that address specifies a particular location, okay, and from that location you take the data out. Okay. And when you want to store the data at a particular address location, that can be achieved by the presence or absence of a data path. That depends upon what kind of circuit arrangement or what kind of a logic arrangement you are using. Sometimes the absence of a active device writes the data, and sometimes the presence of an active device writes the data. Okay. So, you do it from the selected row, your word line. The rows which we have seen in the array are also known as word lines, and the columns in the memory array are also known as bit lines. Okay. So, this is equivalent to a particular device. When we see a device, we are basically referring to the MOSFET, okay, and it is generally the N type MOSFET only which we are referring to. Okay. So, presence of an N type MOSFET might pull down, okay. So, that might be similar to writing a 0, or it might produce a path in such a way that you result in a pull up. Okay. So, that basically means writing a 1 also, right. So, that basically depends. Writing is a process where the device connection is being exploited for that, and reading is simply via a decoder, where you specify the address at the input and you get the location, and from the location you get the output from the ROM. Okay. So, this is one example. This is a 4 by 4 bit NOR based ROM array. Okay. Why am I saying this is a NOR based array? If you see the PMOS devices here, these are your PMOS. These PMOS are connected in parallel, whereas wherever you see NMOS devices, they are generally connected in series. Okay. So, if you remember the NOR, the CMOS implementation of a NOR gate, you would see PMOS devices in parallel and NMOS devices in series. So, this is considered as a NOR based read only memory circuit, and 4 by 4 bit basically means there are 4 rows, 4 word lines and 4 columns or 4 bit lines. Okay. When you want to access a particular row, that particular row has to be given logic 1, okay, and all other rows are to be grounded. So, when you want to access R1, R1 is given logic 1 and all other rows are grounded. And suppose if you want to access R4, here R4 will be given logic 1, right, and all other rows will be grounded. Okay. And how you write 1? This basically works on the column polarities. Okay. So, if you move say from R1, if you see a particular device, okay, if you find an active NMOS there, that is going to provide you a path towards the ground. Okay. So, the presence of an active device is actually going to help you in writing a 0. The absence of an active device is going to help you to write a 1. So, suppose here when you have access to row R1, if you put logic 1 here, this NMOS turns on because the gate is connected to logic 1. Okay. And here if you see an active device connected here, so this becomes like a closed switch. So, this column here C1 gets pulled down towards ground. So, C1 goes to 0, but if you go to the next column, there is no active device here. If you are moving from R1 here, you see an active device here, but you do not see an active device here. If there is no active device here, this point because the gate of PMOS is grounded, this point gets pulled up to VDD. Okay. So, you see a 1 here. So, a presence of an active NMOS device pulls down that particular column and you write a 0. If there is an absence of an active NMOS device there, when you are traversing a row, that basically results in pulling up of that column to VDD, okay, and you write a 1. This is how you program a NOR based read only memory. So, a presence of an active device allows you to write 0, absence of an active device allows you to write 1. Okay. How to access a particular row? You make that particular row equal to logic 1, so that way you access it, okay. And at any given point of time you can only access one row, right. So, that row which you are accessing has to be at logic 1. Right. Now, consider the counterpart of it, which is known as NAND based array. Why this is a NAND based array? You see that somewhere you can see the NMOS circuits are connected here, and your instead of PMOS we are basically using depletion load N MOSFETs. What is a depletion load N MOSFET? Here you connect gate with source, you are basically looking at a 2-dimensional device. So, the requirement for power is reduced, power sources is reduced, it results in a more simpler and a compact circuit. Okay. In this case, whenever you want to access a row, you make it equal to 0. So, if you want to access R1, you ground it. Okay. If you want to access R4, you ground it, and others are kept at logic 1. Okay. So, suppose when you have grounded R1, when you are travelling across R1, when R1 is grounded, this NMOS is off, this NMOS is off, okay, because of logic 0. In any particular column, if you do not see an active device, right, that basically means you are connected to logic 0, okay, because that row when you are accessing it is connected to ground only. Okay. So, here C1 goes to 0, but if you see a device here which is inactive, okay, that part is going to pull up, that depletion load is going to pull itself up to logic 1. Okay. So, presence of a device is going to help you in writing a 1, absence of a device is going to help you write a 0. Okay. So, this is complementary to a NOR based version. You can implement a read only memory using two approaches, one is a NOR based approach, another is a NAND based approach. Okay. In a NOR based ROM, the presence of an active device helps you to write a logic 0, and absence helps you to write logic 1. The opposite is true for the NAND version of a read only memory. Right. To access a row in a NOR version, you have to apply logic 1 to that row. In a NAND based circuit, to access a particular row, you have to apply logic 0 to that row. Okay. In both cases, in both versions, you can only access one row at a time. Right. So, these are two versions, these are two options which are available to us, how to implement a read only memory using NOR version and a NAND version. Okay. Now, this is how you have written the data. How you are going to access a particular stored data, you need some decoding circuits. These are known as row and column decoders. Okay. So, row and column address decoders are designed in such a way that they help you to select a particular memory location in the array, okay, based on a binary row and column address. A row decoder is designed to drive a NOR ROM array. By definition, it selects one of the 2 to the power n word lines, okay, by raising its voltage to output high. Right. So, this is a simple decoder circuit, this is a simple combinational Boolean circuit of decoder. Okay. This is a 2:4 decoder. So, for any n bit address line or any n bit address, you can have 2 to the power n address locations. Okay. So, if you have 2 address bits A1 and A2, you can have 4 different locations. Okay. So, when A1, A2 are 00, right, you can access say row number 1, right. So, 00 address is corresponding to row number 1, 01 is corresponding to row number 2, 10 address bit is corresponding to row number 3, and for 1 combination of address bit you are accessing row number 4. This is a simple decoder circuit which helps you to access the rows in a read only memory. Okay. How you can implement? You can implement it simply like a NOR based circuit only, and the advantage here is that you can implement the memory itself using a NOR circuit, and you can implement the row decoder also using the NOR based circuit. So, both can be fabricated simultaneously in parallel, right. So, if you see this circuit here, A2 is here and A1 is here. Okay. So, this inverter is taking A2 as input and this inverter here is taking A1 as input. Okay. So, here you are getting A2 bar and here A2 is entering, and simply here A1 is entering. Okay. Now, suppose A1 A2 are both are 0. Okay. So, this is 0. So, this is off and this is off, but then A2 bar is 1. When A2 bar is 1, this is on, and when A1 bar is on, this is on. Okay. So, in that case, because this is off and this is off, this NMOS is off, this NMOS is off. When A1 A2 the address bits are 0, this NMOS is off, this NMOS is off, this R1 is connected here to a PMOS whose gate is grounded. Because gate is grounded, this PMOS is always on, right. This pulls itself up to VDD. So, R1 gets selected. Similarly, for 0 1 R2 gets selected, for 1 0 R3 gets selected, for 1 1 R4 gets selected. So, this is a NOR based circuit of implementing a row decoder, okay, which helps you to access the row address location, which row I am going to access. This is for the read operation of a read only memory, right. How I know where I have to read from? So, I need a particular row, I need a particular column. Where these rows and columns intersect, that is my location of reading. Okay. So, for the row decoder I can use a NOR based row decoder circuit, okay, connected in such a way that for n bit address of the row I can have 2 to the power n address locations in the row. Okay. That is for the row element. I can also use a NAND version for row decoder. Okay. It must lower the voltage level of the selected row to 0, because in a NAND version of a read only memory you make the row equal to 0 for accessing, okay, while keeping all other rows at a logic high level. This function can be implemented by using an n input NAND gate for each of the row outputs. Okay. So, you will have a NAND row decoder, okay, which will result in 2 to the power n word lines connected to the NAND ROM array. This is the column part of it. Okay. So, for n address bits you will generate 2 to the power n word lines, and suppose if you have a 2 bit address for 0 0, row 1 goes to 0, others are high. Similarly, if say you have a 1 1 address location, okay, 1 1 2 bit address, then row 4 gets selected by keeping it to logic 0, while all other rows are at logic 1. This is about the row decoding circuit, how you are accessing the rows either in a NOR based circuit or a NAND based circuit. Again, for a NOR based ROM array you can have a NOR based address row address decoder. For a NAND based ROM array you can use a NAND based row address decoder. So, with these decoders you are actually accessing the location of the row. Now, let us just see how you can access the column. For column the circuit becomes even more simpler, you only need to use pass transistors. Okay. So, you take a NOR based same kind of an address decoder, at the input instead of row address bits you are adding or you are entering column address bits. If you have an m bit column address, you will have 2 to the power m bit lines coming from the output. Okay. Each of these lines is connected to a particular pass transistor. Whenever a particular bit line goes high, that pass transistor gets activated and that particular column gets activated. Okay. So, you use a decoder for m bit address, this is about the column, okay, not the row, the column. For an m bit column address, you generate 2 to the power m bit lines. Every bit line is connected to a pass transistor, which is an NMOS pass transistor. So, whenever a particular output of the address column address decoder goes high, that particular pass transistor is turned on, and whenever that is turned on, you activate one of that bit line. Okay. And when you connect, say, both the row and column address decoders together, you can isolate a particular intersection of a row and a column, and that particular cell is what from where you want to read. Okay. And a column decoder does two things. Okay. Your row address decoder does one thing of identifying a row address. Your column decoder does two things. Not only it accesses the column location, but it also helps you to read the output. Okay. So, once you have isolated a particular column, you have identified the column which has gone high, whatever is written on that cell can be connected to the data output. Okay. So, it does two things, it identifies the location in the column, and it also helps you to do the read operation. Okay. So, for the write, you can use a NOR based and a NAND based circuit, right, for writing the data. In a NOR based circuit, you access by making that particular row 1, okay, and for columns you just go by the absence or presence of the device there. Okay. That is how you do the writing part. For reading part, you need decoders. For row, you need a row decoder, which is a simple Boolean decoder circuit only. For an n bit address, you can generate 2 to the power n word lines. For column address, you need a decoder followed by a network of pass transistors, okay, which helps you to find the location of the column and also to read the output from that memory cell. Okay. So, with that, we come to the end of today's lecture. We have introduced the topic of semiconductor memories, okay, which is the most the area consuming and an important part of any circuit, because all the data which you are dealing in a digital system, that is where it is stored. Okay. You need two things, you need a location, which is the address, and you need the actual data which you are either going to read or write. Okay. The operations can be done simultaneously or serially, right. We have discussed the read only memory version, which is a non volatile memory, okay, where data once written remains there and you can keep on reading it. Okay. You have different ways of implementing, either through a NOR based circuit or a NAND based circuit, and for the location you need decoder circuits. Okay. So, with this we end today's lecture. Thank you.